So, as far as determinants are concerned, this is the fourth video, and it's about applications of determinants. So we see how useful determinants can be, having seen their geometric definition, their geometric meaning, that is, how to compute them, their properties, and of course, finally, we talk about the applications of determinants. So, and this will be the last on determinants. Not like we won't have to mention determinants along the line still, but I mean, looking at determinants as a subsection of linear algebra, this is the fourth video, and then we'll talk about other things that we still relate to determinants. Even before we got here, we talked about them too, right? So, in the introduction, determinants have many important applications in mathematics, science, and engineering. They are used to solve systems of linear equations, find areas and volumes, transform variables in calculus, study linear transformations. In this lesson, we study two major applications, like Cramer's rule for solving systems of equations and changing of variables using Jacobians. Okay, so let's go ahead and talk about Cramer's rule. The Cramer's rule is a method for solving systems of linear equations using determinants. It applies when the number of equations equals the number of unknowns. So if you have the number of equations equal the number of unknowns, then we can use Cramer's rule. If not, we can't. The determinant of the coefficient matrix is also not zero. That is, Cramer's rule can only be applicable to non-singular matrices. So the general system is something like this. You have general system in two variables. Consider the system a1x plus b1y equals c1 and a2x plus b2y equals c2. The coefficient matrix will be a1, b1, a2, b2. So matrix A is that. So the determinant, of course, is a1, b2 minus a2, b1, like this. So Cramer's rule now goes this way. First of all, you have computed d, right? So the Cramer's rule for two variables, if d is not equal to 0, that is this a1 minus a1 b2 minus a2 b1 is not 0, then you're going to have x, the x, the solution to this problem, the x is going to be dx over d, and y is going to be dy over d. And then this is the definition of dx. So for dx now, this is the see the original matrix A1, B2, B1, A2, B2. But for dx now, the right hand side C1, C2 replaces A1, A2. For y, the right hand side replaces B1, B2 while retaining the original part. So this is, we had A1, B1, A2, B2. But to get dx, you have for A1, A2, we have it replaced with C1, C2, and then B1, B2 remains. For dy, to get dy, this dy up here. So A1, A2 is retained, but then B1, B2 is replaced by C1, C2. Okay. A very good example is what we have here now. So imagine this, you have this system 2x plus 3y equals 11, x minus y equals 1. So step one, the coefficient matrix is the matrix of all the coefficients 2, 3, 1, minus 1, like this. So the determinant of that is going to be 2 times minus 1 minus 1 times 3, that is minus 2 minus 3, which is minus 5. So you keep that. Now for dx now, so you see for dx, because you need x, so instead of the coefficient of 2, 1 for x now, you replace that with the right hand side, which is 11, 1. But then you retain this 3 minus 1. So you have 11, 1, 3 minus 1. Then you find the determinant. So d of x is minus 11 minus 3 equals minus 14. Okay. So for step 4 now, where you get to find that for y. So again, you maintain 2, 1 here. But since these are the coefficients of y, you replace them with the answer at the right hand side, 11, 1. So for dy, you have 2, 1, 11, 1. So dy is now 2 times 1 minus 1 times 11. That's minus 9. So overall now, to get for the step 5 now, you now put the solutions together. So x is now minus dx over d, that's minus 14 over minus 5, which is 14 over 5. And y is dy over d, that's minus 9 over minus 5, which is 9 over 5. So the final answer is that x is 14 over 5 and y is 9 over 5. So talking about three variables now, we go the same way. So for three variables, you have the system a1x plus b1y plus c1z equals d1, a2x plus b2y plus c2z equals d2, a3x plus b3y plus c3z equals d3. So the main determinant will just be a1, b1, c1, a2, b2, c2, a3, b3, c3, these coefficients now. So the solutions now will be x equals dx over d, y is dy over d, z is dz over d. And of course, we first of all find this determinant, that's d. Then for the other ones now, to find dx, this dx now, you put a1, a2, a3 to replace this, and then all these other ones remain. To find dy, you replace b1, b2, b3 with, I mean, to find dx, right, you replace a1, a2, a3 with d1, d2, d3, right? To find y, you replace b1, b2, b3 with d1, d2, d3, and every other thing remain. Then to find dz, so you replace c1, c2, c3 with d1, d2, d3, and all these a1, b1, all that will remain. And then you can then divide and get your answer. So let's take an example of that. So for three variables here, you have x plus y plus z equals 6, 2x plus y minus z equals 3, x minus y plus 2z is 7. So the main determinant will be the coefficient 1, 1, 1, 2, 1 minus 1, then 1 minus 1, 2, right? You find the determinant there. So that's 1 into, cover this and this, that's 2 minus 1. Okay, that's 2 minus 1. That's 1 into 1. That's 1 there. Then minus 1 into, cover this and this. That is 4 plus 3, right? 4 plus 3, that is 7. So that's 1 minus 7. That's minus 6. Then lastly, you have plus 1 into, cover this and this. That's minus 2 minus 1. That's minus 3, right? Uh, what's that? Okay, this is minus 1, right? So plus minus plus. So plus 1 into minus 2 minus 1. Okay, maybe what I'm just going to do is I'll just go over there and solve this. So we already know the answers are 2 minus 1, 3. So let me just do this to make it to drive the point home as much as I can. So I'm bringing this over here now, and I'm solving that 3 by 3 thing. Okay, so yeah, so I want to solve this now. So we know the original matrix D should be the determinant straight of 1, 1, 1, 2, 1 minus 1, 1 minus 1, 2. Okay, based on all these coefficients we have there. So that's D. So to find D here, I'm just going to go fast. So plus 1 into, cover this and this. So we have 1, 2 minus 1, 1. So that's 2 minus 1, which is 1. So this goes, then minus 1, this 1 now, minus 1 into, cover this and this. So 2 times 2 is 4. 4 plus 1. Yeah, 2 times 2 is 4. 4 minus minus 1. That's 5. Okay. That's 4 plus 1, 5. This is 5 here. Then plus 1 into, cover this and this. That is minus 2 minus 1. So this is minus 3. So that's minus 3. So when we tidy that up, we have D is 1 minus 5 minus 3. So that is why D there is minus 7. So that's D. So on the other hand now, we have to find dx. So for dx, what do? We just replace this 121 with 637, this 637 here. Okay, so we replace that with 637. So we have 637 for the first column, and then every other thing remains the same. So here we have 637. Okay, and we have others 1, 1 minus 1, 1, 1 minus 1, and 1 minus 1, 2, right? So this, every other thing, remember, this 1 to 1 is replaced by 637. So we keep shifting that until we get every other thing we need to get. So dx now is equal to, so again, we still go for plus 6 into, cover this and this, that's 2 minus 1, that's 1. Because that's 1 times 2, 2. Minus 1 times minus 1, that's plus 1. So 1 minus, that's 2. 2 minus 1, 1. Then minus 1 into, cover this and this, we have 6 minus minus 7, that's 13. Okay. And lastly, we have plus 1, this plus 1 up there, into, cover this and cover that. This is minus 3 minus 7, that's minus 10, I believe. So dx is equal to 6 minus 13 minus 10. This is dx 6 minus 23. So this is minus 7. This is 4 here. Is that minus 17? Oh, I hope everything is fine. Let's be sure of that. This is minus 7. This is minus 7 minus 10. Okay, let's check again. So this is 637, right? On the right hand side, 637. So 6 into 2 minus 1, 1. Then minus 1 into cover this and that. So 6 plus 7, 13, yes. Then plus 1 into cover this and that. This is minus 3 minus 7. That's minus 10, which is minus 17. Okay, minus 17. Is that what we have on the other side there? Okay, I guess something is wrong, right? Something is wrong. Where is that again? So dx is minus 7. Yeah, that's fine. This one should be minus 14. So I think something is wrong. So 637, 1, 1 minus 1, then 1 minus 1, 2. Yeah, 637. Okay, let's do this again. So I go 6 into cover this and this. That is 1 times 2, 2. 2 minus 1 is 1, yes. Then minus 1 into cover this and this. 3 times 2, 6. 6. 6. Yeah, 6 plus 7, yeah, 13. Okay. Then lastly, plus 1 into 3 times 2, 6. No, plus 1 into minus 3 minus 7. That's minus 10. So this is 6 minus 23. I still feel something is wrong. 1, 1 minus 1, yes. 1 minus 1, 2. Then 637. 1 minus 1 to 637. Okay, let me check the other side. I know something is definitely wrong. What could that be? So for dx now, okay, I mean everything. Okay, there was a jump here. 1, 2, 1, 1, 1 minus 1, 1 minus 2, 2, 1 minus 1, 2. So this is minus 7 here. So this is minus 14. Okay, I'll check that again. 1, 1 minus 1, 1 minus 1, 2. 1, 1 minus 1, 1 minus 1, 2. And this is 637. So 6, cover this, and this is 1 times 2, 2 minus 1, yes. Then minus 1 into cover this and this. This is 6, 3 times 2, 6 minus 7, that's 13, plus 1 plus minus plus 1 into this and this will go. So minus 3 minus 7. That's minus 10. So I feel something is not right here. Maybe that was wrong. Let me check. Uh, so I guess something is not working right here. Okay. Maybe one way to check is to check if the results work well with the expression. So look at this now. This is 2 minus 1, 3, right? 2 minus 1, 3. 2 minus 1, 3. 2. That's XYZ, right? 2 minus 1, 3. That can be correct. This is 2 minus 1, 3. That's 4. So this should actually be 4. Then 2 again. 4 minus 1, 3. 3 minus 3 is 0. So this should actually be 4. So I think it's better to just change this to 4. 4, 0. Then again 2. 2 minus 1. That'll be 3. 3 plus 3 plus 3. 6. Maybe I think it's better to just make it this way. I think with this, everything makes sense now. Yeah, 406 is better. If the answer is 2 minus 1, 3, then all these ones may even change. So I may have to come back and change this. So let's see how that works first. So yeah, 2 minus 1, that's 1, plus 3, 4, yeah. 2, that's 4, minus 1, that's 3, minus 3, that is 0, okay? 2 minus 1, that's 2 plus 1, 3, plus 2 plus 1, 3, plus 6. Okay, this should be 9. It should be 9. 2 minus 1, that's 2 minus 1, that's 3 plus 6, 9. Okay, so that's 409. So I may have to change this later. Okay, let me come out work on this here. So 409. So this is 4. So this is 4409. Okay. So now I have, because I'm wondering, there's no way that would work. 409. So this can then be 4. This is 1 plus 1. Okay, let me just overhaul the whole thing. Yeah, so we have 4 into cover this and this. 2 minus 1 is 1. Minus 1 into cover this and this. That's 2 times 0, 0. 0 minus minus 9, that's 9. Then plus 1 into cover this and this. Minus 1 times 0, that's 0. Minus 9, that's minus 9 right there. So we have 4 minus 9 minus 9. That is 4 minus 18. That's minus 14. So dx is minus 14. Okay, now that's making sense. Then we go for the next one. We now have dy. So for dy, that's the determinant of the original thing. That's 1, 2, 1. 1, 2, 1. But in the place of the y part, now instead of 1, 1 minus 1, we have 409. So this will be 409. And lastly, we have 1 minus 1, 2. 1 minus 1, 2. Okay, so that we then have dy to be, so we'll do fast again. So this is 1 into cover this and this. This is 0 minus minus this, that's 9 there. 0 plus 9, then minus 4 into cover this and this, that's 4 plus 1, 5. Then plus 1 into cover this and that, that's 18 minus 0. So that we have dy to be 9 minus 20 plus 18. So that's 29 minus 20. No, that'll be 27 minus 20. So dy is minus 7. Is 7, right? So 9 minus 20, that's minus 11 plus 18. That's 7. So we have 7 like that. Okay. Then lastly, we have dz. So dz is determinant. We have the original thing again. 1, 2, 1, 1, 1 minus 1. 1, 2, 1, 1, 2, 1, 1, 1 minus 1, then 4, 0, 9. Okay. So that dz is equal to 1 into cover this and this. That's 9. 9 minus 0, 9. Then minus 1 into cover this and that. That's 18 minus 0. Yes. Plus 4 into cover this and that. Cover this and that. That's cover this and that. That's minus 2 minus 1. That's minus 3. Right? So that dz is equal to 9 minus 18 minus 12. So that's 30 minus 9. dz is 30 minus 9. That's, 9 minus 30, that's minus 21. So that's dz right there. So finally, so we have x to be dx over d, y is dy over d, and z is dz over d. So if you put all that together, dx is minus 14. That's minus 14. D itself is minus 7. That's the original D we got here, minus 7. Okay. So that's so this is 2 now. Then we have dy. dy is 7. So that's 7 over minus 7, which is minus 1. And lastly, z, which is dz over d. So d, that's minus 21 over minus 7, which is equal to 3. Okay, so that's equal to 3. So finally, we can say that x, x, y, z is equal to 2 minus 1, 3. 2 minus 1, 3. And that is the answer there. That's how Cramer's rule goes rather. So what do we have here now? So I may have to adjust some of the values here. So this is 2 minus 1, 3. Okay, this is, yeah, minus 14 over minus 7. Okay, now this works perfectly. So I think everything works well now. Yeah, everything works well now because minus 14, 7 minus 21, right? Minus 14, minus 14, 7 minus 21. Yes. So that works now. If it's 409, then we are good. Yeah, so that's Cramer's rule, and that's one usage of determinants. So we can also use determinant for change of variables, uh, like as stated before. So, okay, I guess I have to look at this step by step. So in calculus, changing variables simplifies integrals. For instance, let x be x, which is a function of u and v, and y is a a function of u and v. Then we integrate with respect to u and v instead of with respect to x and y. So, and the Jacobian can help us with that. So the Jacobian determinant is such that we have j, which is d of x comma y over d of u comma v, and that is dx du, du dv, dy du, dy dv. So this is very good for dynamical systems and or system of equations. So j now is now dx du times dy dv minus dx dv times dy du. So this is the now determinants of this Jacobian. So that's the Jacobian determinant. And then we have area transformation. When changing variables, dx dy is the same thing as the absolute of the Jacobian multiplied by du dv. So the Jacobian then corrects the change in area. All right. So let's try that out and see how that works. Imagine that you have x equals u plus v and y is u minus v. So we can have step one, take the partial derivatives. So the x du, partial x, partial u, that's differentiate x with respect to u, that's 1. Partial x, partial v, you get 1, 2. Partial y, partial u, that's also 1. Partial y, partial v, that's minus 1 because this is negative v. So after doing that, you now put the Jacobian together. You have dx du, dx dv, dy du, dy dv. Okay, so you have 1, 1. So the Jacobian is the determinant of this. That's 1 times minus 1, that's minus 1. Minus 1 times 1, that's minus 1 again. So minus 1 minus 1, that's minus 2. The absolute value of j is 2. So with that in place now, we have the Jacobian, which corrects the change in area. And then we can talk about an example talking about integral transformation. Imagine you want to evaluate the double integral of x plus y dx dy. So, and you are given that x is u plus v, y is u minus v. So, yeah, and the region is u lying between 0 and 1, and v lies between 0 and 1. From 0 to 1, u is from 0 to 1, v is from 0 to 1. Then you can convert integrand. So, to convert the integrand, right, you can have x plus y. So, if you add the two together, right, x plus y is equal to 2u, v minus v will go. So you have x plus y equals 2u. That's you converting the integrand. Then you can then transform the integral. So you have double integral x plus y dx dy equals integral from 0 to 1, integral from 0 to 1 of 2u. Okay, so x plus y, now you know x plus y is 2u. So you have 2u here. Then dx, so you want to convert to du dv, right? So you know that if you differentiate, this is now dy right here. So if you differentiate dy, so dy is now 2u dv. So you have, this is 2u already here. So x plus y now, you have 2u for x plus y. Then dx, if you differentiate dx, you get 2 du. And then if you differentiate dy, dy, okay, is it where we come to for this? Yeah, we need dx, right? Dx, dx du is equal to, dx du is 1, right? So the x is just equal to du. And then dy for dy now. So everything boils down to integral from 0 to 1, integral from 0 to 1 of 2u to du dv. And then you have integral from 0 to 1, integral from 0 to 1 of 2u times 2, that's 4u du dv. And then you can then do your integration. Integral from 0 to 1 of 4u du, that's integrate 4u, you have 4u squared over 2, that's 2u du. That's 4u squared, right? That's 4u squared over 2. That'll be 2u squared. If you put 0, 1, you get 2. Integral from 0 to 1 of 2 dv, you also get 2. So the final answer in this case is 2. So you can easily do that change of integral in this case if you are given all this. Then we can also do the same for polar coordinates. You can do the transformation. X is r cos theta, y is r sin theta. So the Jacobian in this case is j equals r. That is, if you do the whole dx dr dx d theta dy dr dy d theta. So at the end of the day, you have dx dr is the Jacobian times dr d theta and all that. Okay, I suspect I need to do that. X is r cos theta, y is r sin theta, right? X is r cos theta. So see, x is r cos theta. X is r cos theta. Y is r sin theta. So we need to do the Jacobian. So the Jacobian is okay, that hasn't changed. The Jacobian is the determinant of partial x, partial r, partial x, partial theta, then partial y, partial r, partial y, partial theta. Okay, so in that case, now the Jacobian is equal to partial x, partial r is, so partial x, partial r is equal to cos theta simply. Okay, so that's cos theta right here. Partial x, partial theta. So partial x, partial theta is equal to, differentiate cos theta, you get minus r sine theta. You know, if you differentiate cos, you get sine. So that's minus r sine theta. Okay, then here you have partial y, partial r, which is simply r sine theta, which you have down here, r sine theta. Then next you have partial y, partial theta, which is r cos theta. So this is r cos theta. So the Jacobian now is simply cos theta times r cos theta. So that's cos theta into r cos theta minus r sine theta into minus r sine theta. Okay, there was minus there before, so you have another minus outside. So this is r cos squared theta. Minus and minus is plus r squared sine squared theta now. So is equal to j is equal to is everything fine here? So j now is equal to what's different here now? Cos theta. Hmm. What could this be? Cos theta. We have an r cos theta. Differentiate theta. Hmm. R cos squared theta plus r squared sin squared theta. R, we have cos theta. Theta, we have minus r sin theta. Then dy dr. Aha, dy dr should just be sin theta. Okay, I think that's my fault there. This is just sin theta. So dy dr is just sin theta. So that's my fault here. This is sin theta. So we have sin theta. Okay, this is just sin theta into, so this is just r sine square theta. Okay, that makes life easy. So we can factorize r into cos square theta plus sine squared theta. So that's, this is, the whole thing here is 1. So that goes to 1. So we just have j to be r. Okay, So if j is r, then we can just have that the new, so it means that the x, the r, or the x, the y, that where we're coming from, is just equal to the absolute of j, the r, the theta. And j now is r, so that's just simply r, the theta. So that helps us to change from the Cartesian coordinates into the polar coordinates like that. And that's what happens over here. So the x, dy is r, dr, theta. So for polar integral, now we can try this. We have double integral of x squared plus y squared dx dy. So the region here we have x squared plus y squared is less than or equal to 4. So we can convert, right? We already know x squared plus y squared equals r squared. We can do the conversion. Dx dy is r dr d theta, as we know already. So for step 2 limits, now we have r lies between 0 and 2, and theta lies between 0 and 2 pi. So based on, if we do all the conversion, so we then integrate, we have integral from 0 to 2 pi, integral from 0 to 2 of r cubed dr theta. So integral from 0 to 2 of r cubed dr is 4. Integral from 0 to 2 pi 4 d theta is 8 pi. So the final answer is then 8 pi. So in summary, we have that Cramer's rule solves linear systems and requires determinants not to be zero, then works best for small systems, then change variables, uses Jacobians, correct area distortion, and simplifies integrals. The key formula is that dx dy is equal to j du dv, that all the new coordinate system we want to go into. Then we have practice questions. You can use Cramer's rule for this if you tried that before. So Cramer's rule can work for this too. Then 3 and 4, Cramer's rule still works for all of these ones. The Cramer's rule can work for a system of 3. I've done a 3 by 3 system, so you can also do this too. Then part C now, find the Jacobian of the transformations. Of course, so Jacobian of transformation, just okay, I think I'll do number 8 because that looks not so familiar. So UV and U over V, I'll do that later. Then for number 10, change the variables in integral. So you want to do that based on what we did previously and evaluate using polar coordinates. So let me do 8 where x is uv and y is u over v. Want to do the Jacobian uh trans the Jacobian of the transformation. So yeah, like that. So I come here now and do the Jacobian to find the Jacobian, find the Jacobian of the transformation of the transformation. That's x equals uv, right? And y is u over v. X equals uv. So x equals uv and y equals u over v. Of course, u over v is the same thing as uv raised by minus 1. So that's a nice way, an easier way to represent that. So we can say that the Jacobian now is equal to partial x, partial u, then partial x, partial v here. Then we now have partial y, partial u, and partial y, partial v. That's what the Jacobian looks like. So the Jacobian now is now partial x, partial u. Differentiate x with respect to u. You have v left here. Okay. Partial v, partial x, partial v. You have u left here. And then for the other one, partial y, partial u, you have v inverse here. Then partial y, partial v. Now that's multi-layered. So it's like we're differentiating with respect to this. So we can use a quotient rule, right? So uh partial y, partial v. So that's okay, we fixed v, right? So differentiate v. So we have u here multiplied by, for v, we have bring down the power minus 1. Then the original v that was there, we have v raised power minus 2. Reduce the power by 1. Okay, bring down the power, reduce the power by 1. So I think that's about what we have. So J now should then be, I hope nothing is wrong there. So let me know in case anything is already wrong. I doubt it though. So VU, uh, V inverse, then minus UV raised by minus 2. So Jacobian now is the determinant. So we have the determinant that's V into minus UV raised by minus 2 minus UV inverse. So that J is equal to minus UV raised by minus 1 minus UV raised by minus 1 again. So it's like the same thing, so that we then have J to be minus 2UV raised by minus 1, so that J finally is minus 2U all over V. So, of course, if we want the determine this one, we have minus 2U over V. That is 2U over V like that. I think that should be what that is. So with this, we come to the end of this interesting video about the applications of determinants as we see its use in um in Cramer's rule and change of variables, talking about Jacobian. All right, so try your hands on the questions and see how well you have mastered these concepts. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you very much for doing that. If you haven't subscribed, the question is why? What are you waiting for? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can as well also become a member of the channel by clicking on join, and that gives you some special privileges. Like you get to see some videos first. Some videos are only made for you as a member. You can request for my PDF, my PDF notes of these things I'm teaching. You can actually hang out with me. I can consult for you depending on your level of membership. We can talk about anything that interests you on my channel, be it mathematics, data analysis, data science, machine learning, scholarships, writing books, anything at all that interests you on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.